Ever watched water boil and wondered how something so simple feels so complicated? It's not just bubbles rising. It's a high-stakes physics party where heat, fluid, and phase changes collide. Today, we're unraveling how scientists are finally cracking the code on boiling, thanks to a revolutionary AI model called Bubbleformer. Let's dive in. Boiling isn't just a kitchen chore. It's a critical process in everything from power plants to space suits. But predicting it. Historically, it's been like trying to predict a hurricane with a broken barometer. Traditional models rely on simulations that take days to run on supercomputers, and even then, they struggle to capture the chaos. Why? Because boiling isn't just about heat. It's a dance of three phases: liquid, vapor, and the ever-shifting boundary between them. Think of it as a three-ring circus, where every ring is constantly changing. Enter Bubbleformer, a game-changer in fluid dynamics. This AI doesn't just guess what happens next, it understands the rules of the boil. How? By learning from vast datasets of boiling scenarios, it acts like a neural network with a superpower. It deciphers the language of bubbles. Imagine a team of experts, each focusing on a different part of the puzzle: temperature, velocity, bubble shapes, while keeping track of how everything evolves over time. Here's the magic. Bubbleformer uses a technique called transformers, the same tech behind your favorite language models. But instead of translating sentences, it translates the physics of boiling. It employs tricks like factorized axial attention. Think of it as zooming in on a bubble's surface while still seeing the whole pot, and frequency-aware scaling, which helps it handle rapid changes, like a bubble bursting in a split second. The result? Predictions that are faster, more accurate, and adaptable to any fluid, from liquid nitrogen to refrigerants. But how do we know it works? The researchers didn't just test it on pretty simulations. They created BubbleML2, a massive dataset capturing boiling in every possible way. From tiny bubbles in a pool to turbulent flows in a pipe, this dataset is the ultimate stress test. And Bubbleformer crushed it. It outperformed old models, especially when predicting the future, like guessing where a bubble will form before it even pops. This isn't just about faster computers. It's about understanding chaos. Imagine cooling systems that adapt in real time, or spacecraft that manage heat without relying on gravity. Bubbleformer could make these ideas a reality. And as the researchers say, it's not just about speed. It's about decoding the invisible rules that govern how liquids turn into vapor. So what do you think? If AI can predict boiling, what other complex systems could it crack next? Hit subscribe for more deep dives into the science shaping our world, and let's keep exploring together. But boiling isn't just about bubbles. It's also about the invisible boundaries between liquid and gas, where sudden jumps in pressure and velocity create mathematical nightmares. Ever wondered how a pot of water knows exactly when to boil, or why some liquids sizzle violently while others just bubble gently? It's all about the invisible dance of bubbles, and the math that keeps it from falling apart. Today, we're pulling back the curtain on a clever trick called the ghost fluid method, and how it helps scientists tackle one of the trickiest problems in fluid dynamics: sudden jumps in pressure and velocity at the boundary between liquid and gas. Imagine you're watching a movie, where a character suddenly teleports from one room to another. The camera would glitch, right? That's kind of what happens when you try to model a boiling liquid. At the moment a bubble forms, the properties of the fluid, like pressure and velocity, change instantly. Traditional math struggles with these sharp jumps, leading to errors or crashes. Enter the ghost fluid method. It's like a digital magician that creates a ghost version of the fluid on either side of the interface, letting the equations handle the transition smoothly. Think of it as adding a buffer zone where the math can breathe, so the simulation doesn't break when the real-world physics get wild. But how does this tie into something as everyday as boiling? Well, when a liquid boils, bubbles form at tiny sites on a heated surface. The frequency of these bubbles, how often they pop off, directly affects how efficiently heat is transferred. Scientists call this the wait time, the brief moment a bubble clings to the surface before it detaches. Predicting this wait time is key to designing better cooling systems, from microchips to space missions. Take liquid nitrogen, for instance. Its low surface tension means it boils more readily at lower temperatures, creating a frenzy of tiny bubbles. Water, with its higher surface tension, forms fewer, larger bubbles. These differences aren't just academic. They're critical for machine learning models trying to predict boiling behavior. It's like teaching a computer to recognize patterns in a chaotic, fluid world, where every drop has its own personality. To test their models, researchers used a tool called FlashX to simulate a lab setup with FC72, a common refrigerant. By matching real-world conditions, like heat flux and fluid properties, they showed their simulations could replicate complex flow regimes: bubbly, slug, annular, even dryout. It's like a virtual laboratory where the rules of physics are rewritten in code, letting scientists explore the invisible mechanics of boiling without ever lighting a stove. From AI-driven predictions to mathematical tricks that tame chaos, the science of boiling is a testament to human ingenuity. Whether it's cooling a supercomputer or keeping astronauts safe in space, these breakthroughs are shaping the future, one bubble at a time. What other mysteries of the physical world will we unravel next? Stay curious.